All right, so this is part 2 of the angled launch projectiles notes. What we're going to do in part 2 is learn how to calculate the change in position of a projectile that's launched at an angle. So let's revisit this cannonball example. Let's say a cannonball is launched at a 45-degree angle, and let's also say that it's launched at a speed of 80 meters per second, very fast. This cannonball is going to have two different components to its speed. It's going to have a horizontal component of 56.5 meters per second. And what that means is that that cannonball horizontally is going to move 56.5 meters every second. There will be no change in this. There will be no slowing down or speeding up because horizontally, projectiles move at a constant speed. So every second, that cannonball is going to move to the right 56.5 meters. Now vertically, that cannonball is going to start out with an initial speed of 56.5 meters per second as well. However, that speed is going to change. Remember, projectiles accelerate vertically. They accelerate by negative 9.8 meters per second squared. So that means that this cannonball at first is going to slow down vertically, and then at the peak it will be at rest vertically, and then after the peak it will start to speed up as it accelerates towards the ground. So in order to calculate the vertical position of this cannonball, I'm going to have to keep in mind that the speed is always changing. So my vertical position is one that has to be calculated. And the equation that we're going to use is actually one that we've used before. Whenever we've talked about dropping projectiles or horizontally launching projectiles, we've used this equation. Our change in position vertically is equal to 1/2 acceleration times time squared. And remember, we've talked about how this 1/2 acceleration is really 1/2 of 9.8, which ends up becoming about 4.9. We determined this in our video analysis lab, actually. But what are we going to do when projectiles are thrown with an upward speed, like this cannonball? It's launched at an angle, and because it's launched at an angle, it has an initial upward speed. We're going to have to add a piece to this equation that we've never used before, and that piece looks like this: VI times time. Now, VI stands for the initial vertical speed. So this 56.5 meters per second initial vertical speed is what I would substitute in for VI. And then time is just the moment in time we're trying to solve for the cannonball's vertical position. So this is the only new piece. And again, we're only going to use this when projectiles are thrown upwards, whether it's thrown upwards at an angle or even just straight upwards. So let's get some practice using these two equations. So let's say a projectile is launched at a speed of 40 meters per second and a 30-degree angle. I need to figure out what my initial vertical speed is and my initial horizontal speed is. So I'm going to draw this really quick. So it's launched at a 30-degree angle like this and a speed of 40 meters per second. So my horizontal speed looks like this, Vx, and my vertical speed looks like this, Vy. Now you might have started to notice a pattern as we did these examples in part 1 that Vy, maybe I should zoom in so it looks a little bit neater. You might have noticed that Vy always equals your hypotenuse times the sine of your angle. And that's something that we can assume is always going to be true. So if you wanted to skip some of the steps to work that out, just for the sake of time, that's fine. And then Vx is always equal to our hypotenuse times the cosine of 30. So I'm going to plug these two into my calculator and see what I get for my horizontal and vertical speed. So 40 times the sine of 30 gets me 20, and then 40 times the cosine of 30 gets me 34.6. Okay. So my vertical speed is 20 meters per second initially, and my horizontal speed, I forgot already, was it 34.6? Yeah. It's 34.6 meters per second. So if I want to figure out my positions horizontally and vertically of my projectile, I need to keep in mind that my horizontal speed is constant. So that means that my horizontal position changes by a constant amount. So if my starting position is 0, and my horizontal speed is 34.6 meters per second, that means that horizontally, I'm going to move 34.6 meters each second. So from 0 to 1 seconds, I'll move 34.6 meters. From 1 to 2 seconds, I'll move another 34.6 meters. And I think that's going to get me 69.2. I'm fairly certain. Let me plug that in the calculator. 34.6 plus 34.6 gets me, 69.2. So that's how I would go about calculating my horizontal positions. I would just always be adding 34.6 meters every second. My vertical positions are going to need to be calculated using the equation that we just learned on the previous page. So I'm going to rewrite that equation over here where I've got some space. So that equation, and this is an equation that will be given to you, so you don't have to memorize it. But that equation is change in position equals 1/2 acceleration times time squared plus initial velocity times time. Now remember, I only use this part of the equation if I'm working with a projectile that was launched upwards at all in any way, even a little bit upwards or directly upwards. So if this is an instance where it's launched upwards, I need that part, which it is. So I'm going to plug in what I know to start finding my positions. I know that my vertical position starts at 0. If I want to figure out where my vertical position was at 1 second, I would need to plug in 1 second in for my time, and any other quantities that I know as well. I know that the acceleration of gravity is negative 9.8 meters per second squared. The negative is going to matter because negative means down, and my initial velocity is up, which means it should be a positive value, whereas my acceleration should be the opposite sign because it's down. So we're going to make sure that we use negative 9.8. My time, if I want to find 1 second, is going to be 1. My initial vertical speed, my VI, this is what I solve for with my SOHCAHTOA. So 20 will be what I plug in for VI, and then 1 second is my time. So I just need to plug this in my calculator. I think I can actually do some of it in my head. So I know that 1/2 times negative 9.8 is negative 4.9. And 1 squared is just 1, and anything times 1 is itself. So that means this is going to be plus 20. Then I just need to do that in my head. This would be 15, except there's minus an additional 0.1. So I think it would be 14.9 meters per second. Oh, wait, no, meters. Meters, because this is my initial, this is my position. If I were solving for speed like this, then my answer would be in meters per second. But since I'm solving for a position, like a Y position, my units are just meters. Good thing I caught that. So my initial position, or my position at 1 second, I should say, is 14.9 meters. So now let's do it again for 2 seconds. So same equation, same calculation, but this time I'm going to plug in 2 for my time. So negative 9.8 for acceleration, but this time it's going to be 2 squared plus 20, because that's still my initial speed, times 2. So my delta y is going to equal negative 4.9. This is going to be times 4. That's a lot tougher. Plus 40. Let's figure out what's negative 4.9 times 4. Times 4. That's 19 point. So I'm going to get negative 19.6 plus 40. So that would be 20.4 positive. 20.4 meters. Okay. So that would be my position at 2 seconds. Oops. So that's how I go about finding the positions of a projectile at different moments in time, horizontally and vertically. So the next one is a try, because we technically did like kind of 3 examples because we filled in 3 points in the data table. Go ahead and try to start finding the horizontal and vertical positions, the horizontal and vertical positions in this table. If you're ready to check your answers, unpause the video. All right, I'm going to assume if you're listening to this, that means you are listening and checking your answers. So let's get started by figuring out what the speeds are of this projectile. So it's launched at a 45-degree angle, which looks something like this. I know that my horizontal speed is going to equal my vertical speed, because this is a 45-degree angle, and that makes an isosceles triangle. Now I know that the hypotenuse of this triangle is 40, so I just need to technically solve one time, but I'm going to solve both times just to be sure. I know Vy is going to equal 40 times the sine of 45 degrees. And that should equal the same thing as my horizontal speed, which is going to be 40 times the cosine of 45 degrees. So let's see what I get. So 40 times the sine of 45, and then let's do 40 times the cosine of 45 and make sure I get the same thing. Yep, 28.3. So my horizontal speed is 28.3 meters per second. My vertical speed is also 28.3 meters per second. So horizontally, I'm going to start at 0, and my position is going to change by 28.3 meters per second every second. So 28.3 plus 28.3, I think I can do that in my head. I know it's going to be 0.6, it'll be 6, I think 56.6. Yeah, 56.6. So these are my horizontal speeds. I love finding horizontal speeds because it just moves at a constant amount every time. So it's a constant change every second. So I don't really need an equation to do that. I'm just adding 28.3 every time. But my vertical position is going to have to be calculated with an equation. I know it's starting at 0, but I need to use my delta y equals 1/2 at squared plus vit. So let's solve for my vertical position at 1 second. So hopefully you plugged in negative 9.8 for your acceleration. If we're solving for 1 second, we'll plug in 1 for time. And hopefully you use 28.3 for your initial vertical speed. So now I just need to simplify this. So I'm going to get negative 4.9 plus 28.3. Can I do this in my head? I think I can. 28 minus 5 would be 23. but there's a 0.1 there, so that would be 1 greater. So it would be 23.1 plus the 0.3 there, so 23.4 meters. I don't trust that I'm doing my math right. Let me do this in the calculator. 28.3 minus 4.9. Did I do that right? Yeah, I did. Look at that. I'm proud of myself. Okay, so 23.4 is my speed, or my position, my vertical position at 1 second. I'm going to do the same thing now at 2 seconds. So delta y equals 1/2 negative 9.8 times 2 squared plus 28.3 times 2. So my delta y equals negative 4.9 times 4 plus, oh gosh, this will be, oh, I know, I just got that 56.6. I got that from over there. And then 4.9 times 4, I just did in the calculator. That was like 19.6, yeah. So delta y equals negative 19.6 plus 56.6. So that is really just like 56 minus 19, which is like 56 minus 20, which would be 36. But you have the 1, so it's 37 meters. Yeah, So 37 would be my vertical position, 37 meters. So that concludes part 2 of this video. So now we know how to calculate both our horizontal position as well as our vertical position. And remember, the only one that requires an equation is the vertical position, because horizontally we're moving at the same speed every second. So we should change our position by the same amount every second, which isn't really much of an equation.